I will now start this video presentation by explaining about the introduction for the soil improvement and stabilization. Soil improvement, also referred to as soil modification, is an important practice in construction engineering used to enhance the engineering properties of natural soils so that they can safely support structures. In many construction projects, existing soils may not possess sufficient strength, stability, or durability, which can result in excessive settlement, cracking, or structural failure. Soil improvement techniques are therefore applied to modify soil properties such as strength, compressibility, permeability, and workability. The main objectives of soil improvement include increasing soil strength, reducing voids, controlling permeability, and preventing erosion. Improving practical bonding enhance the soil's ability to withstand applied loads, while reducing voids minimize compressibility and settlement. Where voids cannot be completely eliminated, filling methods help reduce water movement and soil instability. Soil improvement is widely applied in foundations, embankments, road subgrades, slopes, and working platforms to ensure uniform load distribution and long-term structural stability. With increasing construction on sites with poor ground conditions, soil improvement remains a vital component of modern construction engineering.
I will explain a type of soil improvement method. So before starting any construction project, understanding soil conditions is crucial because natural soils may not always support structures adequately. To improve soil performance, several methods are commonly used, especially for soft or saturated clayey soils. Broadly, soil improvement techniques are divided into four categories. First, soil improvement without admixtures, which includes methods like soil replacement, preloading, vertical drains, and sand or prefabricated drains to enhance drainage and reduce settlement. Second, soil improvement with admixtures or inclusions such as stone columns, which densify the natural soil and provide additional support. Third, stabilization using additives and growthing method including chemicals, cement, lime, and fly ash stabilization as well as jet growthing to strengthen soil and reduce compressibility. Lastly, thermal methods like soil heating and freezing can significantly alter soil properties, though these are most costly. Overall, the choice of method depends on the soil type, project requirements, and desired performance.
Assalamualaikum, my name is Muhammad Amir Hafiz and now I will explain about the typical construction process of soil improvement and stabilization technique. The first step is site investigation and soil identification. In this step, it is to identify soil type and ground condition and to determine bearing capacity and settlement risk. The second one is selection of soil improvement method. In this step, it is to choose method based on soil condition and match technique to project requirements. The third step is site preparations. It includes site clearance and debris, level ground and remove unsuitable soil, and prepare access for machineries. The fourth one is execution of soil improvement work. Selected improvement technique will be applied, and soil will be treated systematically and uniformly. And in this step, the soil will be improved of its strength, stability, and stiffness. The fifth step is quality control and testing. In this step, it will monitor the construction process and conduct field and lab tests. And in this step also, it will verify soil strength and performance and ensure compliance with design requirement. And the last step is monitoring and observation. In this step, settlement and ground movement will be observed and to detect potential ground issues early and to confirm the effectiveness of improvement.
Now I will explain the materials and equipment used in soil stabilization. Materials include Portland cement to strengthen soil, lime to stabilize clay and reduce moisture effects, granular materials like sand and gravel to improve structure, and drainage and geosynthetics such as geotextile and geogrid for long-term reinforcement. Equipment includes excavators to prepare the site and place materials, soil mixer to mix soil with cement and lime evenly, lists and compactors to achieve proper density and stability, and water tanker to control moisture, add compaction and manage dust.
This slide shows the standard procedure of soil improvement. First is site investigation. Soil tests such as SPT, CPT, and laboratory tests are carried out to identify the soil type, strength, and groundwater condition. This helps engineers to choose the suitable stabilization method. Next is the site preparation. The site is cleared from vegetation and rigged topsoil, and underground utilities are identified to ensure safe construction. Then stabilization application is done. The selected method such as chemical or mechanical stabilization is applied. Materials like cement or lime are mixed into the soil, followed by compaction and curing. Finally, compaction and quality control are carried out. The soil is compacted in layers and field tests are done to make sure the required strength and quality are achieved.
I will now continue by explaining about the project background for the two case study, which is Tunaza Exchange and Marina Bay Sands. Tunaza Exchange is a large-scale mixed-use development located in the heart of Kuala Lumpur, planned as Malaysia's International Financial District, strategically positioned near Jalan Tun Razak and integrated with an MRT interchange station. TRX offers excellent accessibility and connectivity. The project integrates office towers, residential buildings, retail spaces, hotels, and public areas within a single urban precinct to promote efficient land use. With an estimated gross development value and overall contract sum of approximately 40 billion ringgit, TRX reflects its national importance. The project is owned and master developed by TRX City Sdn Bhd under the Ministry of Finance Malaysia with key consultants and contractors including Arup Group Limited, IJM Corporation Berhad, and WCT Holdings Berhad. Next, for Marina Bay Sands. Marina Bay Sands is a landmark integrated resort located at Bayfront Avenue in Singapore's Marina Bay, developed to support the nation's long-term economic, tourism and urban growth. The project integrates hospitality, retail, entertainment and commercial functions, comprising three hotel towers connected by the iconic Sands Sky Park, along with a casino, convention and exhibition center, shopping mall, theatres and museums. With a total contract sum of approximately USD 5.5 billion, it is one of the most expensive integrated resort developments globally. The project was developed by Las Vegas Sands Corporation with Moshe Safdie as the lead architect, support by international engineering consultants, contractors, and project managers to address complex structural and geotechnical challenges on reclaimed land.
Next, I will explain about type soil and its properties for these two case study. At the Tun Razak Exchange, TRX site is a former mining area consisting mainly of soft clay and silt. These soils have low bearing capacity, high compressibility, poor drainage conditions, and contain organic matter, which makes them unsuitable to support heavy structures without improvement. For the Marina Bay Sands site, on the other hand, is reclaimed land over soft marine clay and alluvial deposits. These soils are highly compressible, retain a lot of moisture, and have low shear strength, making construction challenging and prone to settlement. In both projects, for TRX and Marina Bay Sands, soil conditions require careful soil improvement and foundation treatments to ensure stability and long-term structural safety before any major construction takes place. For this slide, I will explain the soil improvement and stabilization technique that apply at the project sites, which are Tun Razak Exchange and Marina Bay Sands. At Tun Razak Exchange, which was previously a mining area, the soil condition was soft and unstable because of clay and silt at the project site. Therefore, techniques such as deep ground treatment, mechanical stabilization, and grouting were used to improve soil strength, control ground movement, and enhance overall stability. And for the next case study project, Marina Bay Sands, the site was located on soft marine clay. Methods including preloading with vertical drains, deep soil mixing, jet grouting, and bolt pile foundations were implemented to accelerate consolidation and provide adequate load support. These techniques ensure the soil can safely support structures and help minimize long-term settlement and structural risk.
Next, we move to material used for soil improvement and stabilization. For TRS project, there are three materials. One of them is Portland cement. It acts as a chemical stabilizer, increase soil strength and rigidity, and reduce settlement and permeability. The second one is sand, gravel, and crushed stone. It used as granular material for stone columns. It improves soil load bearing capacity and rigidity, and also accelerate consolidation and reduce pore water pressure. The third one is geotextile. It is a permeable synthetic materials and used with stone column and soil replacement work. It prevents mixing of granular material and fine soil. The second one is Marina Bay Sand Project. There are three materials used also. The first one is lime. It is suitable for green clay soils. It reduces soil plasticity, improves workability, and lowers moisture content. The second one is Portland cement. It is used in jet grouting and deep soil mixing, and it increase soil strength and rigidity and reduce settlement and permeability. The third one is granular material. It is mainly used for subcharge loading, and it used to apply additional vertical stress to accelerate consolidation process of soft clay. Now we have construction techniques used for soil improvement and stabilization. For the Tun Razak Exchange or TRS project, soil improvement focus on soft and weak ground conditions. Techniques such as deep soil mixing were used to mix cement with in situ soil to increase strength and reduce settlement. Vibro displacement and replacement, also known as stone columns, improve bearing capacity and ground stiffness. In addition, prefabricated vertical drains with preloading were applied to accelerate consolidation of soft clay. And for the Marina Bay Sands project, ground improvement was carried out mainly on reclaimed marine soil. Preloading with PVD was used to speed up consolidation and control long-term settlement. Vibro displacement helped improve soil strength and drainage, while jet grouting was applied to increase load-bearing capacity and reduce permeability. Overall, both projects use different techniques based on site conditions to ensure foundation stability and structural safety.
Next, I will explain the testing and monitoring in TRX and Marina Bay Sand. At TRX, lab tests check soil classification, plasticity, strength, and compressibility. Field tests, like standard penetration tests and plate load tests, verify soil strength. On-site monitoring with settlement plates, slope meters, and sensors track ground movement and pore water pressure for stability. At Marina Bay Sand, standard penetration tests and pile load tests confirm soil and pile performance. Settlement monitoring ensures threatened soil maintains strength under real loads. Continuous monitoring in both projects allow yearly detection of issues, ensuring safe and effective soil stabilization. Next, I will explain the problems occurred in both case studies. At the TRX site, soft soil caused uneven settlement and weak foundation support, limestone formation, and a high groundwater table further increase excavation difficulty and stability risk. At Marina Bay Sands, deep soft marine clay had low bearing capacity and caused long-term consolidation, settlement under heavy structural loads. This issue requires effective soil stabilization, ground improvement, and continuous monitoring, which will be explained in the next section. Solution to the problems.
This slide shows the problem-solving method used in construction project, especially at Tun Razak Exchange and Marina Bay Sand. So for Tun Razak Exchange, the main soil problems are soft soil and high groundwater level. The first is pile foundation is used. Piles transfer the building load to hard soil layers, which reduce settlement and improve stability. Second, stabilization is also applied. Lime stabilization strengthens the weak soil, reduce settlement, and improve the bearing capacity. Lastly, the dewatering method is used to control the groundwater. Routing fills cracks and cavities in limestone, which improves soil stability and site safety. Ensure the building at TRX are safe, stable, and durable. So for the problem solving for Marina Bay Sand, the main challenges are heavy building loads and weak marine soil. A deep foundation system is used for this project because reinforcement concrete, both piles and barrette piles support heavy loads and provide long-term stability. Deep soil mixing is applied. The soil is mixed with cement binder in situ to increase strength and stiffness. It is suitable for urban areas because of low vibration. Jet grouting is also used because high pressure grout strengthens the weak soil. Also improve pipe performance and reduce groundwater seepage. This solution ensures Marina Bay Sand remains stable and safe despite difficult soil conditions.
This slide explains the similarities and differences between the TRX project and Marina Bay Sands in terms of soil conditions and engineering solutions. Firstly, looking at the similarities, both projects were constructed on weak ground with low bearing capacity and high compressibility, which pose a high risk settlement. Because of this, both projects required soil improvement measures and deep foundation systems to control settlement and ensure structural safety. For the techniques such as preloading with vertical drains and board or pile foundations were used to improve ground performance before construction. However, there are clear differences between the two projects. The TRS project was located on a former mining area where the soil was highly disturbed, non-uniform, and contained loose materials. Therefore, ground replacement, mechanical stabilization, and grouting were necessary to strengthen the soil and improve uniformity. In contrast, marina basins were developed on reclaimed coastal land with deep layers of marine clay. Due to the thickness and softness of the clay, more extensive treatments such as deep soil mixing, jet grouting, and deep pile foundations were applied to transfer loads to stronger strata. In conclusion, although both projects face similar challenges related to weak soil, the different site conditions directly influence the choice of soil improvement and foundation methods.
Now I will explain the effectiveness and efficiency. For the TRS project, ground improvement focused on efficiency, cost and suitability for large urban development in Malaysia. Deep soil mixing was used to improve deep soft soil and silt by mixing cement slurry with in-situ soil, increasing bearing capacity and reducing excessive settlement while protecting nearby structures. Vibro displacement and replacement, or stone columns, were installed using a vibrating probe to strengthen soft soil, improve ground stiffness, and control settlement. PVD combined with freeloading accelerated consolidation of soft clay by shortening drainage path and reducing long-term settlement. In some areas, excavation and replacement remove unsuitable shallow soil and replace it with compacted granular material to provide immediate bearing capacity improvement. Monitoring mainly involve standard site investigation and SPT tests. In contrast, the Marina Bay Sands project required much higher performance due to reclaimed marine clay and extremely heavy iconic structures. Preloading with PVD was extensively applied to accelerate consolidation and control long-term settlement. Vibro replacement installed compacted granular columns to improve soil strength, drainage capacity, and pore water dissipation. Jet grouting was used to inject high-pressure cement grout, significantly increase load-bearing capacity and reducing permeability with careful pressure control to avoid ground movement. MBS also carried out extensive load testing, SPT, and long-term monitoring to ensure excellent control of total and differential settlement. Overall, TRX achieved sufficient improvement with higher efficiency and lower cost, while MBS prioritized maximum effectiveness, superior settlement control, and long-term reliability.
Next, I will explain the cost comparison between TRX and Marina Bay Sands. TRX costs around 555 million and use standard soil improvement methods like vertical drain, stone columns, cement and sand with routine lab and field testing. The project includes office, retail, hotels and residential towers with moderate materials usage and manageable grades. Marina Bay Sands costs around 37.6 billion. It requires advanced soil improvement, including cement lime stabilization, jet grouting, and deep soil mixing, along with extensive testing and long-term monitoring. The project includes hotels, shopping malls, entertainment venues, and convention centers with high material usage and complex construction. Overall, Marina Bay Sands had higher costs due to larger scale, advanced soil treatment, extensive monitoring, and iconic structure.
In conclusion, this case study examines the soil improvement method employed at Tun Razak Exchange and Marina Bay Sands. Both projects encountered soil-related issues, including soft soils, high groundwater level, and settlement risk. To overcome these challenges, methods such as pile foundation, soil stabilization, jet grouting, and deep soil mixing were applied. TRX mainly used deep piles and soil stabilization due to limestone soil. The Marina Basins applied deep piles, jet grouting, and deep soil mixing on reclaimed land. Overall, proper ground improvement ensures structural stability, safety, and long-term durability of the building. That's all from us. Thank you.